Hello, welcome all together. Now, this is our officially last and final exercise sheet, number 4. Due to the chapter numbering in the script, this is called exercise sheet number 4, and it's about sequences and series of numbers, which will later be extended to functions again, terms and functions combined in the way, in the form of a series, which is, as you know, the summation of a certain number sequence, one after the other. And if you introduce a variable x again, this is a very interesting method to make approximations to important functions, as you may know. So this is actually, this whole topic here is a preparation for things like Taylor series, potency series, and so on. So let's just have a look. And there are some exercises inside here which are more like, let's say, warm-up, okay? Warm-up calculations to get along with the arithmetics of fractions and potencies and factorials and so on. So don't wonder why some of these exercises are not really exactly speaking about sequences. More or less, some preparatory warm-up exercises also are to be found here. Okay, so let's jump into my handwritten solution. Okay, back again once more. If you look at the first series here, sequence, sorry. So this is, of course, there is not very much annotation here, but you can imagine that this expression should be evaluated for n starting with, usually with 1, sometimes with 0. It's not really clear, but more interesting is the question, how does this expression behave if n approaches infinity, if n keeps growing and growing and growing? So that's what we do most of the time. So what do we see here? This is a factorial in the denominator of the number n minus 1. Remember that these are natural numbers. And then something like a super exponential, you could say. Please note that the basis term and the exponent both are ascending with n, and the same is true here, n to the n. So if you compare them, this one is a little bit higher, of course, but the difficult question will be, how do they behave in combination? Also, there's another factorial here of a number n plus 1. So if you analyze this, now you could start with your factorials, you will find out, of course, the expression in the denominator here, in the denominator is all the time bigger, a little bigger at least, than the one here. But how do you exactly get this in a simpler form? And well, before I explain it in a too complicated way, let's just take an example. So it seems that always the term in parentheses here in the numerator is lower than here in the denominator, and the difference of these two numbers in parentheses is 2, of course. So an example would be, we have 6 factorial divided by 8 factorial, and so it's easy to see that the whole factorial in the numerator, sorry, is contained in this one. You can completely cross it out and remove all the factors inside here from here, and everything that remains is or are the 2 biggest factors of the denominator factorial, which are in this example case 7 times 8. So that's clear, because this is the multiplication 6 times 5, or let's start with 1 times 2 times 3 times 4 times 5 times 6, and that's it. And all these factors are also contained here. So it seems easy to see that now, going back to the symbolic notation, the factor that remains here is firstly n plus 1, which is the largest, would be the factor of 8 in this example. and also the factor of 7, which corresponds to a factor of n. So that's what I do. I cross this out, and then I cross out the, well, the exclamation sign here, just to say the factor of n plus 1, yes, will be kept. And then I put the factor of n here. So everything that stays is n times n plus 1. That's all. And here it's not so easy, because if you remember all our laws of potency, there is none of them which can be easily used if you have different bases and different exponents. So there are some laws for a common basis term. In the case of a fraction, this is called the, as far as I know, it's called the third. Yes, no, actually the second law of potency. And the fourth one, on the other hand, takes different bases but same exponents. So that's a little bit a problem. Now I have to make a little break, just too short. So let's proceed. Now there's quite an easy trick to get rid of this plus 1 here in the exponent. That's much more easy than transforming the bases. You know, it's almost impossible to transform this expression so that n plus 1 is in the basis, neither to transform this one so that n is in the basis, but the exponent can easily be adapted, so that if I cross out this plus 1, you know what it means by the first law of potency. It means I can split this up into n plus 1 to the power of n times n plus 1 to the power of 1. So there is a single factor of n plus 1 which I remove by crossing out this plus 1 here. And that means I can also shorten it or reduce it using this n plus 1 in the denominator. And so this disappears, even this disappears, and then I get here n plus 1 to the power of n, this one, simply, and n to the n in the denominator, and also this additional factor of n, you know, it came from the shortened factorials. So now if we just put this aside as a factor of 1 by n, what remains is I may pull out this exponent of n outside of this fraction. So I, just for clearness, I put this in parentheses. So actually it's the same as n plus 1 divided by n and then to the power of n. Now, if you don't recognize this term, probably you wouldn't at first sight, it's the best you can do is to split up this fraction, which you can always do if it contains a sum in the numerator, as you all know. So I can split this into n by n plus 1 by n. Then it looks like 1 plus 1 by n, and then the whole expression, this quantity, to the power of n. So now, hopefully, this is familiar to you. You have encountered this expression probably when talking about exponential functions or exponential terms, whatever. And then you should recognize it as a part of the definition of Euler's number. Actually, that's the official definition of Euler's number if you take the limit of this expression for n approaching infinity. You may know this. If not, it's at first sight, it's a little surprising because you see that the basis term tends or approaches 1, but coming from numbers bigger than 1. You can just, for example, 1 plus 1 for n equals 1, and then I get 1 plus 1/2, 1 plus 1/3, but with very big numbers for n, I will get something like 1 plus 1 by a million, and so on. You know? So it approaches 1, but from above, while this one, of course, approaches infinity. And that's like something of the sort 1 to the power of infinity. And as you know, also by the famous rules of L'Hopital for looking for limits of functional terms, fractions, and so on, 1 to the something of the sort 1 to the power of infinity is a difficult case because it could it could be limited. It could also approach 1. It could also diverge to infinity. Fact is, the limit, it's a hard task to show it cleanly, but in the end, this is exactly what tends to be Euler's number. So this is an important conclusion, because only if we can be sure that this term does not diverge, okay, it does not tend to something like approach infinity, it stays limited. And that's the reason why this factor of 1 by n dominates the whole procedure. Understand what I mean? So I can split up the, that's a general rule of taking the limit, you know that I can take the limit of one factor times the limit of the other factor. But if it were the case that this one approaches infinity, we would have a case of 0 times infinity, which is again a very difficult case. This is not the case here. Here this stays limited, and this one clearly approaches 0. Okay, so that means in the end, the limit of the whole expression is 0. So that's not really quite an easy example. On the other hand, if we had just slightly modified by saying from the start, we would have said this is n to the n minus 1. Then this would compensate the factor of n. It would disappear at this place, and then the limit of the whole expression would be Euler's number, E. So that would perhaps even be a little nicer still, but it's just like some of the others, it's like more like a warming up example, okay? And okay, anyway, then we can proceed to this one, which I modified a little bit from the original version, because then it gets more interesting. If you look at this fraction, you will note that it's not so really easy to guess. Why is it? Well, no, you see the square root of n plus 1, if you compare it to the square root of n, and you are thinking of very big natural numbers n approaching infinity, it might be, and actually it will be the case, that the difference between these two square root expressions gets lower and lower and lower, so that in the end the difference is almost 0 for very big numbers n. And if this is the case, you can assume that the whole expression in the denominator approaches 0, so that the constant here, 1 divided by something that gets even smaller and smaller and smaller, it might be that the whole expression diverges to infinity. And actually it does, but how to show this in a very straightforward way? Now, something which you may know is there are some methods for putting a fraction in a form so that the denominator is rational. That's quite a standard procedure, so you might have the idea to use it. It's always by using the third binomial formula. So what do? We regard this to be something like a, expression a, and here b, so it's something like a minus b. Then we expand the whole fraction by using and multiplying the other compound of the third binomial formula, which is called a plus b. You see what I mean? A minus b multiplied by a plus b. This is the scheme. And by this scheme, we all know that the result is a squared minus b squared. So that's what I'm doing. I'm expanding this whole fraction this way. So if you look here, you can see what I get. It's quite nice, because my a square corresponds to the square of this root. So the root sign disappears and it stays n plus 1. I put it in parentheses just for clarity. Then I get minus b squared, where b equals square root of n. So also this root sign disappears and n stays there. So then if I remove the parentheses, I have n minus n, which means the 1 remains. It's in the end, it's just a simple 1 staying here. But in the numerator, I get a combination of these square roots with a plus sign instead of a minus sign between. So that's fine, because this is almost done. You could, I think also if it were yet, an examination question, I think Martin would allow you to say, so this is obviously growing infinitely, although the square root is taken. So it doesn't, of course, it doesn't grow as much as n itself, but it grows. This is, the square root is a monotonously rising operation. And so this one grows and this one grows, and since they are both positive with a plus sign added up together, it's quite obvious that this whole thing approaches infinity. But I made, just for your interest, I made some little transformations to make it even clearer. So what do? I put this n as a factor outside of this expression, and then so it's like taking 1 plus 1 by n in parentheses and then times n. You see, if you remove the brackets here or the parentheses, you get n plus n times n by 1. Sorry, n times n by n times 1 by n. This is what I wanted to say. So in the end, you get n plus 1. So that's an yes, a possible transformation. Why do I do this? So that I have a root of n here and a root of n here, and then I can do similarly. I can put it in this form. You see, in parentheses now, I drew this factor of n outside. Also, I split up this square root, of course, to a root times root. So like root times root of n times root of the parentheses. So that's what I'm doing here, okay? So in the parentheses, it stays the square root of 1 plus 1 by n. And then also, since here's it's square root of n, putting this outside, I'm getting plus 1 in the parentheses. So that's it. And now I make a little substitution. I say u equals square root of n. So then the whole thing gets at least some sort of a polynomial form. It's not really because there's the root sign, but I get polynomial expressions inside, which is a little bit easier to argue about. Okay, so this is here my factor of u, and here square root of 1 plus now it's 1 divided by u squared, of course, because if I use this, u squared will be equal to n. Everything's positive, so we don't have to care about this, about the sign, plus 1. And now finally I could do the following. I could say the limit of the whole sequence, which I call bn, will be, after this substitution, also the limit of this newly built sequence, which I now I just rename it to be called b, and then this serpent symbol here, b serpent, let's say index u. Why is it? Well, it's just because this is quite a different term in comparison with the original term, so that's why I just rename it. But anyway, important point is, if n approaches infinity, also u approaches infinity. So that's fine. And then I get limit u approaching infinity. U itself, of course, approaches infinity for this part, and then multiplied by the limit of this expression. And finally, I can say that here, this clearly approaches 0. Yeah, that's no question. So the whole square root expression approaches square root of 1 in the end, which is 1. And then going further, this parenthesis term approaches 2. And so, but in the end, this means, since this is a limited expression multiplied by something with a limit of infinity, whole expression approaches infinity, and that means it's divergent. So that was, I know this was a little bit complicated and not really necessary if you can also you can already argue that these two will diverge. So, but in the end, the conclusion of all this is that the denominator of the original expression approaches 0. If you look here, so that means that the difference between between the roots of two neighbored numbers, natural numbers, tends to be almost 0 when n approaches infinity. So that's what it's about. Okay, let's just jump to the next one then.